The first type of calculation we're going to look at is the formula mass or the relative molecular mass, which can be abbreviated to MR. So the information we need to use is what we'd find on the periodic table. So in this example, what is the formula mass of sodium oxide Na2O? We look at sodium and oxygen on the periodic table, and we're going to be using their mass numbers. So the mass of the whole molecule is going to be the mass of sodium, which is 23. But we've got to remember we've got 2 atoms of sodium. So we'll add that in again, plus the mass of the oxygen atom, and that comes to 62 is the formula mass or relative molecular mass of sodium oxide. Here's another question to try for yourself. What is the formula mass of HNO3 nitric acid? And this is the information you'd be able to look up on the periodic table. So pause the video, have a go at the question, then see how you've got on. So this time we've got 1 hydrogen atom and its mass is 1. We've got 1 nitrogen atom and its mass number is 14. And we've got 3 oxygen atoms, so that will be 3 times 16. And when we add all of that together, we get 63 for the formula mass of nitric acid. If during this video you feel like you need a bit of extra practice, go to my C4 playlist and you'll find extra examples on each of the calculations that I'm showing you. The next calculation I'm going to show you is one called conservation of mass. And conservation of mass means keeping the mass the same. So whatever mass of starting chemicals or reactants that you start with, that turns into the products, but the total mass of the products is the same as the total mass as the starting reactants. So if we take this example of copper oxide reacting with hydrogen to make copper and water, if we start with 40 grams of copper oxide and 1 gram of hydrogen, that could make 32 grams of copper and 9 grams of water. Now if we add up the total mass of reactants, we can see we're starting with 41 grams of chemicals, and the products it changes into, we've got 32 grams of copper, 9 grams of water, so that's 41 grams of products. So we can see from this example that the mass of reactants is equal to the mass of products. Here's the typical question you could get on your exam. 16 grams of copper reacts with oxygen when it burns to produce 17.5 grams of copper oxide. What mass of oxygen did it react with? And you'd be provided with the symbol equation. So the best technique to answer these questions is to annotate the equation with the information we've been given. So we know we've got 16 grams of copper, and it's going to produce 17.5 grams of copper oxide. And we've got to remember that the starting mass of all the reactants is equal to the mass of products that we get at the end. So both sides have to add up to 17.5 because the mass of the products is 17.5, so all of the reactants together need to add up to 17.5. So the missing number is going to be 17.5 minus 16 grams, which is 1.5 grams. So 1.5 grams of oxygen reacted with the copper. And if you want to check we're correct, 16 plus 1.5 is 17.5, the mass of reactants, and we've got 17.5 as the mass of products. So we can see we've got conservation of mass. Very often the exam questions about conservation of mass involve a practical burning magnesium. So first of all, we find the mass of magnesium using a balance, and the mass of magnesium in my case is 0.13 grams. We then also weigh an empty crucible and lid that we're going to burn the magnesium inside. And this time the crucible and lid is 25.27 grams. We then heat up the magnesium inside the crucible, and every now and then we lift up the lid to let more oxygen get into the crucible. As oxygen enters the crucible, it reacts with the magnesium to form magnesium oxide. So we should see that the mass increases because at the start we were just weighing magnesium atoms, but when the magnesium is joined with the oxygen to form a compound, magnesium oxide, the mass should have increased. And there's the white magnesium oxide powder in the bottom of the crucible. The crucible and lid is then reweighed along with the magnesium oxide inside, and we can see that the mass has increased to 25.51 grams. So the exam question could be set out like this. They'll describe the experiment with the diagram that I've just showed you, and they would say the mass of magnesium at the start was 0.13 grams. The mass of the empty crucible and lid was 25.27. When the magnesium was placed inside and burnt in oxygen, the mass went up to 25.51 grams. And the first question for 1 mark would be, calculate the mass of magnesium oxide. Well, all we need to do for that is we've got the mass there of the magnesium oxide along with the crucible and lid. So all we need to do is subtract the crucible and lid. And we get 25.51 take away 25.27 is 0.24 grams. So that's the mass of magnesium oxide. And then the second part of the question might be calculate the mass of oxygen that reacted with the magnesium. So this is where we need to use conservation of mass. And remember that the total mass of the reactants is the same as the total mass of the products. So we know the mass of magnesium, so like before, we're going to annotate the equation with the masses. So that was 0.13 grams. And we know now the mass of magnesium oxide that was produced. That was 0.24 grams. So the product comes to 0.24, so the reactants need to come to 0.24. So to find the missing number, 0.24 take away 0.13 is 0.11 grams. And as a final double check, we add up these two, we get 0.24, so that's the mass of the reactants, and that's also the mass of products. So conservation of mass has happened. I'm going to make up a copper sulfate solution by dissolving 0.76 grams of copper sulfate into 200 centimeters cubed of water. And then I'm going to show you how we could calculate the concentration of this solution. To work out the concentration of that solution, we need to remember the formula. Concentration is the mass of the solute in grams, so that's the mass of the copper sulfate powder that I put in, divided by the volume of the solvent, in this case the water, in dm cubed. So that's the important part, it's in dm cubed. So we need to remember 1 dm cubed is the same as 1000 cm cubed. And to go from cm cubed to dm cubed, we divide by 1000. So let's put the numbers that I measured into this formula. Concentration is mass in grams. Well, I weighed out 0.76 grams of copper sulfate, and that's divided by the volume in dm cubed. So the 200 centimeters cubed, I divided by 1000 to get 0.2 dm cubed. And when we work that out, it comes to 3.8. And the units are going to be grams slash dm cubed. Grams per dm cubed. Here's a question for you to try yourself. Work out the concentration of blood glucose if a patient had 0.2 grams of glucose in 100 centimeters cubed of blood. So pause the video, have a go yourself. Here's the equation to get you started. So from the question, we can see that the mass in grams is 0.2 grams of glucose. But did you remember to change the 100 centimeters cubed into dm cubed by dividing by 1000? And when you do that, we get the volume is 0.1 dm cubed. So when we calculate this, 0.2 divided by 0.1, we get 2, and the units are going to be grams per dm cubed. From this point on in the video, it's strictly for higher tier only candidates because we're going to start doing calculations in moles. And moles are really a way of counting how many atoms or ions or molecules you've got. So if you've got 1 mole of something, we've got 6.02 times 10 to the 23 atoms or ions, whatever it is you're looking at. And we call that number the Avogadro number or Avogadro constant. If we're dealing with atoms on their own, for example, an element, then we can calculate moles using this formula. Moles is the mass in grams over the AR, which is the relative atomic mass. So to find this, you would look up the mass number on the periodic table. So, how many moles in 50 grams of sodium? So we've got 50 grams here is the mass. The relative atomic mass of sodium is 23. So 50 divided by 23 is 2.17 moles. Have a go at this one yourself. How many moles are in 10 grams of magnesium? So to work it out, you should have done 10 divided by 24 because we've got 10 grams and the mass number on the periodic table for magnesium is 24. That's its relative atomic mass. And when we do the calculation, we get 0.42 moles. If we're trying to work out the moles of a compound, this is the formula we use. Moles equals mass over mR. And remember, mR is the relative molecular mass or the formula mass. So, how many moles are there in 40 grams of H2O? So we remember moles is mass over mR. First of all, we've got to work out the mR or formula mass of water. Well, oxygen is 16 plus the 2 hydrogens gives us a mR of 18. The mass is 40 grams over 18, and that comes to 2.22 moles. Try and work out this question for yourself. How many moles are in 20 grams of NaCl? Once again, we use the formula moles equals mass over mR. And the mass is 20 grams. The mR is going to be 23 for sodium plus 35.5, which is 58.5. And that comes to 0.34 moles. I'm now going to show you how to work out the concentration of a solution in moles per dm cubed. We've already come across how to work it out in grams per dm cubed, where we use the formula concentration is mass in grams divided by volume in dm cubed. There's a lot of similarities here. Concentration this time is moles divided by volume in dm cubed. So let's look at an example. What is the concentration if 20 grams of BeCl2 is dissolved in 0.3 dm cubed of water? So, to work out the moles, it's our equation we've come across before. Moles is mass divided by mR. The mass is 20 grams. And if we work out the mR of BeCl2 by adding up the mass number of Be and then the same for 2 lots of chlorine, that comes to 80. So 20 divided by 80, the number of moles is 0.25. So coming back to the concentration, concentration is moles divided by volume in dm cubed. So that's going to be 0.25 moles divided by 0.3 dm cubed. And the answer we get is 0.83, and the units are going to be moles per dm cubed. Have a go at this one yourself. Work out the concentration in moles per dm cubed if 8 grams of calcium oxide are dissolved in 25 centimeters cubed of water. And notice this is in centimeters cubed, so it will need converting to dm cubed first. So before we forget, we'll change this 25 centimeters cubed into dm cubed by dividing it by 1000. So that becomes 0.025 dm cubed. We then need to work out the number of moles of the calcium oxide, and we do that using the formula moles equals mass over mR. So we've got 8 grams of it, and the mR, well, the mass number for calcium is 40, 16 for oxygen, so the formula mass or relative molecular mass is 56, 40 add 16. When we do 8 divided by 56, we get 0.143 moles. We put that into the concentration equation. Concentration is moles divided by volume in dm cubed. So we've got 0.143 moles. The volume now in dm cubed is 0.025, and that comes to 5.72 moles per dm cubed. So well done if you got that one correct. I'm now going to show you how you can use moles to calculate the mass of products. So the first example is what mass of sodium oxide is made from 20 grams of sodium, and they will provide you with the symbol equation in the question. So first of all, we look at the big balancing numbers in front of the two things that we're interested in, and we can see a 4 and a 2, and that tells us that 4 moles of Na makes 2 moles of Na2O. So we need to work out how many moles of sodium we've got, and we do that using the familiar equation moles equals mass over AR. It's AR this time because we've just got atoms of it, sodium on its own. So the mass is 20 grams and the AR of sodium is 23. That's just the mass number of sodium from the periodic table, and that works out at 0.87 moles. So if 4 moles of sodium makes 2 moles of sodium oxide, that's a ratio of 2 to 1, so you just half it. So then to get the number of moles of sodium oxide, we half 0.87, and that gives us 0.435 moles. But we need to change that into a mass in grams. So we rearrange the equation and we get mass is moles times mR. So that's going to be 0.435. But now at this point we need to work out the formula mass or relative molecular mass of sodium oxide. So that's going to be 23 plus 23 for the mass numbers of both sodiums, plus 16 for the mass number of oxygen, and that comes to 62. We put that into our previous equation, mass is moles times mR, and that gives us an answer of 26.97 grams. So here's one to have a go at yourself. So pause the video, have a go and see how you get on, then resume the video. So this time the question is what mass of magnesium chloride is made from 10 grams of magnesium? And we're given the equation once again. This time we can see, because there's no balancing numbers in front of the formula we're interested in, we can see that just 1 mole of Mg makes 1 mole of MgCl2. Now we need to work out how many moles of magnesium we've got in that 10 grams. So moles of magnesium is mass over AR, which is 10 over 24, and that comes to 0.42 moles. Now in this question we've got a ratio of 1 to 1. So if we've got 0.42 moles of magnesium, we're going to make 0.42 moles of magnesium chloride. But we need to change it into a mass. So mass of magnesium chloride is moles times mR, so that's 0.42. And then we need to work out the mR of magnesium chloride, which is going to be 24 plus 35.5 for each of the 2 chlorines, and that comes to 95. So we put that into our equation, and the answer we get is 39.9 grams. Now, if you need a bit more help at some of these questions, go to my main playlist, which is C4 calculations, and you'll see there's some more of this type of calculation to help you out. We're now going to start working out the limit in reactants and reactants in excess, and many students find this a bit easier than the last calculations we've just been working on. So first of all, the limiting reactant is the one that runs out first and causes the reaction to stop. The reactant in excess is the one that's left over once the reaction has stopped. So if we have 20 grams of chlorine and we add it to 100 grams of potassium bromide, which is the limiting reactant and which is the reactant in excess? So first of all, we work out the number of moles of each reactant. So the moles of chlorine is mass over mR, so that's going to be 20 over 71. If you're still struggling to work out the mR, then rewind the video to the part where we do that. And that comes out at 0.282 moles. The moles of KBr is mass over mR again. So this time it's 100 grams over 119, and that works out at 0.840. We can see from the equation that with the balancing numbers we need twice as much KBr compared to Cl2 because we've got that big 2 in front of KBr. And we can see from those numbers we've got more than twice as much KBr. So that means the chlorine is the limiting reactant, that will run out first, and there'll be plenty of potassium bromide left over, so KBr is the reactant in excess. Here's a question to try for yourself, so pause the video and have a go. 70 grams of iron oxide is added to 12 grams of hydrogen. Which is the limiting reactant and which is the reactant in excess? This time we can see we need 3 times as much hydrogen compared to the iron oxide when we look at the equation. So we'll work out the moles of each. Moles of iron oxide is mass over mR, so that's going to be 70 grams divided by 160, and that comes to 0.44 moles. The mass of hydrogen is 12 grams divided by 2, which is 6 moles. At this point, I'll point out that it's divided by 2 rather than 6 because that big 3 in front of it we ignore when working out the moles, because the mR is only ever for one molecule, so H2 rather than 3H2. So we can see it's a ratio of 1 to 3. That means if we have 0.44 moles of iron oxide, multiply by 3, and that gives us 1.32 moles of hydrogen. So in a perfect world we'd have 0.44 moles of iron oxide and 1.32 moles of hydrogen, but we can see we've got a lot more than 1.32 moles. We've actually got 6 moles of hydrogen. So hydrogen is in excess, and that means the iron oxide is the limiting reactant. The next type of calculation we're going to cover is moles to balanced equations, and if you're finding the video useful so far, please do give it a like. Okay, so 496 grams of silver sulfide decomposes to produce 432 grams of silver and 64 grams of octasulfur. Work out the moles of each and use this to balance the following equation. So the first thing we do is we annotate the equation with the masses we've got. We write those underneath each formula. And then to work out the moles, it's the same equation as always. Moles equals mass over mR. So for silver sulfide, it's going to be 496 grams divided by the mR, which is 248. So that's 2 moles. For silver, it's going to be 432 grams divided by 108. That's 4 moles. And for the sulfur, it's going to be 64 grams divided by 256. And that's 0.25. Now, at this point, you might be able to spot the ratio, but if you can't spot the whole number ratio, what we're going to do is divide it by the lowest number to help us. So we will do 2 divided by 0.25, 4 divided by 0.25, and 0.25 divided by 0.25. And that gives us a whole number ratio of 8 to 16 to 1. And then what we do is we rewrite the equation with those balancing numbers in front. Of course, we don't write the 1, we don't need to write that. So it becomes 8 Ag2S turns into 16 Ag plus S8. And if we do a double check, that all balances on each side. So here's one for you to try for yourself. 204 grams of NH3 reacts with 480 grams of O2 to produce 360 grams of NO, 324 grams of H2O. Work out the moles of each and use this to balance the following equation. So pause the video while you try it yourself and then check back in with the video. First thing we do then is we annotate the equation with the masses, and then we work out the moles of each part of the equation by using moles equals mass over mR. So for NH3, that's 204 over 17, which is 12 moles. For O2, that's 480 over 32, which is 15 moles. NO is 360 over 30, which is 12 moles. And H2O is 324 over 18, which is 18 moles. And then to help us reduce this down to a whole number ratio, we divide by the lowest number again. So we divide all of those by 12. And then that becomes 1 to 1.25 to 1 to 1.5. But we can't have, for example, 1.25 oxygen molecules or 1.5 water molecules. We need to get it to a whole number ratio. So first of all, we'll double it, see if that works. That becomes 2 to 2.5 to 2 to 3. Then we'll double it again, and it becomes 4 to 5 to 4 to 6. So we've got the simplest whole number ratio. So all we do then is we could either rewrite the equation with those numbers in front, but in this case I'll simply add those numbers to the formulas in the equation. So if you found this video useful, please do subscribe. Thank you for watching.